Continuing with Chapter 15, we're going to talk about independence. So we know that independence means that the outcome of one event will not affect the outcome of another event. Flipping a coin, doesn't matter if it lands heads or tails, it will not affect how a dice will end up when you roll it. We can actually mathematically determine if two events are independent based off of conditional probability. If events A and B are independent, then the conditional probability of B will equal the regular probability of B. Using the notation, we would have the conditional probability, so this is the probability of B given A, but this is still just calculating the probability of B. That has to equal the overall probability of B. The reason why this works is because if two events are independent, then they won't affect each other. So knowing A will not affect the probability of B. So in the conditional probability, we know A here. If they're independent, then this probability shouldn't change just because we know A. For example, we want to find out if the probability of having good grades as a goal is independent of gender of the responding student. So to find out if getting good grades versus gender is independent, we calculate the probability that getting good grades is equal to the probability of getting good grades given we know their gender. Now they're not being specific here, so we can just say being a boy. The probability of getting good grades is the 247 out of the 478. So 247 over 478. And if they're independent, that should equal the probability of having good grades given you're a boy, which would be the probability of good grades and boy, all over the probability of boy. So here, now we're going to be looking at boy and good grades out of just the boys. So that would be 117 out of 227. And again, if they're independent, they will be equal to each other. So 247 out of 478 is 0.517, and that should be equal to 117 out of 227, which is 0.515. In this case, I would consider these to be independent. So they're not off by that much, but we would want them to be exactly the same. Now, what about for sports? Are sports and gender going to be independent? So in this case, again, we would find out if the probability of sports is equal to the probability of sports given the gender. Last time we did boys, so this time let's just do girls. And again, in both cases, we're calculating the probability that their goal is to play sport. However, in the first one, it's out of the grand total. So sports, 90, out of the grand total, 478. For the conditional probability, we're still finding the probability that the goal is to be good at sports. But now we're given a condition. We know that they are a girl. So again, the conditional probability would be the probability of sports and girl out of just the girls. So sports and girl is 30 out of girls, 251. So if we calculate the percentages, again, we would want them to be exactly the same. So the probability of just being good at sports is 0.188. And then the probability of being good at sports given you're a girl is 0.120. These two do not equal each other, therefore being good at sports and gender are not independent. And the reason why here is because the probability that you select a student and they're good at sports is 18.8%. But if you know they're a girl, the probability goes down to only 12%. So knowing one condition affects the outcome of the other. Therefore, they're not independent. Depending on independence. It's much easier to think about independent events than it is to deal with conditional probabilities. So make sure when you do multiply probabilities that the events are truly independent, because if they are not, you will have to use the conditional probability. We've talked about independent and disjoint, but we want to talk about how they are actually related. Are disjoint events independent? They are similar ideas, but disjoint events cannot be independent. Consider two disjoint events: getting an A in this class and getting a B in this class. They are disjoint because they have no outcomes in common. You cannot have both an A and a B. You will have one or the other. But if you know that you're getting an A, does that affect the outcome of getting a B? And it does, because if you know you're getting an A, then that means that there is a 0% chance of getting a B. Whereas before you know what you're getting, you have a chance that you could be getting an A and you have a chance that you could be getting a B. But once you know, it changes the probability. Therefore, they are not independent. For example, looking at drunk driving again, we were told that 78% of drivers pulled over on suspicion of drunk driving get a breath test, 36% get a blood test, and 22% get both. So the first thing we want to know, are they mutually exclusive? Meaning, are they disjoint? Well, we're told that 22% can get both. So disjoint means that they share no outcomes in common. And in this case, because 22% do get both, they do have outcomes in common, and therefore they are not disjoint. You can also tell this if you were to make a Venn diagram, because when you make the Venn diagram, if they overlap and you can put a percentage on the inside, then they are not mutually exclusive. For our second example, we want to know if the two tests are independent. So, does the fact that you get a breath test affect getting a blood test? So, in this case, I would make a table. So to make the table, we just plug in the numbers that we already know. The total is 100%, the probability of getting a blood test is 36%, probability of a breath test is 78%, and then we know that the probability of getting both is 22%. And then we just have to add and subtract to fill in the rest of the table. So in this case, 36 minus 22 is 14, 78 minus 22 is 56, 100 minus 36 is 64, and 100 minus 78 is 22, and then 22 minus 14 is 8. So once I have the rest of the table filled in, I can then determine, are the two tests independent? So in order to do that, I would find out if the probability of getting a blood test is equal to the probability of getting a blood test given a breath test. Now you could do it the other way around as well and find the probability of a breath test and determine if that's equal to the probability of a breath test given a blood test. Either way, you should end up with the same percentages in order for them to be considered independent. So the probability we get a blood test is 36%. Then we have to calculate the probability of getting a blood test given a breath test, which would be the probability of both, so blood test and breath test, out of just the breath test. So that ends up equaling probability of both, 22%, out of the breath test, 78%. The probability of 22% out of 78% is 28.2%. So again, these are not independent because the probability of getting a blood test is 36%. But if you know that you've already had a breath test, the probability of having a blood test goes down to only 28.2%. Therefore, having one does affect the outcome of having the other. The other thing you can do is kind of think about things in context. Does it make sense that they would be independent or not? And in this case, it's not, because you can be given a breath test on the side of the road, but they have to take you to the doctor to get the blood test. And they're not going to do that unless you fail the breath test. So if they give you the breath test and you pass, you don't get a blood test. If they give you the breath test and you fail, then you get the blood test. So you can always think about it in context as well. But that is all I have for tonight, and I will see you guys tomorrow. Have a good night.